Okay, we've talked about some of the boundary behavior and interference of waves in general terms. Now we're going to look at traveling waves versus standing waves, and then also talk about how standing waves are formed. And so that's the path we're heading towards right now. Let me change my ink color. Much better. Okay. So a wave travels through a medium. We can see a crest moving along from particle to particle, and we got crest. And we got troughs, and that happens. And what we see is what we call a distinct wave pattern. We call it a sine wave traveling through the medium. Now this continues to move uninterrupted until it encounters another wave along the medium, or a boundary with another medium. Now we've talked about both of those. The wave pattern that is seen traveling through a medium is called a traveling wave. So any wave pattern we see, that sine wave, is called a traveling wave, or a traveling medium. Now, what is a standing wave pattern? However, it is possible to have a wave in a space in a medium and still produce a regular wave pattern that is discernible amidst the motion of the medium. So when we have a proper frequency, we can have waves that will reflect and bounce and interfere, okay? And we can have interference such a matter that there are points along the medium that appear to be standing still. So it's like if all these waves, all these different colored waves, met at a point where their frequencies were there, what we'd see is all these particles would appear to be standing in one spot, and we call it a standing wave. So a standing wave is where all the waves, where interfering waves meet to produce a regular wave pattern. That is, we cannot tell that there's more than one wave in that medium. Okay, so now how these form? Well, a standing wave pattern, again, is a pattern caused within a medium, okay, where the vibration or the frequency causes the waves from one of the medium to interfere with the incident waves from the source. So reflected waves and incident waves interfere. Now this interference occurs so that they appear to be standing still. So they do meet in phase. Now because this pattern is characterized by points that appear to be standing still, this pattern is often called a standing wave pattern. Now this is only found, and these patterns are only found at specific frequencies. These frequencies are known as harmonic frequencies, or we call them harmonics. When we get into sound, we'll talk about harmonics some more. So at any frequency, other than the harmonic frequency, the interference leads to a disturbance in the medium that is irregular and non-repeating. But when there is this interference, that's where we start to see the harmonics occur. So let's talk about a standing wave and how it's formed. You did the wave reflection simulation. But if we're at a fixed end and we send a wave or a pulse, the pulse will go to the fixed end, and then as it reflects off, it will become a trough. So it'll be upside down, it'll be inverted, right? Now if we take two pulses and send the first pulse through, and as it reflects on another pulse back, they will meet at some point. Okay? And then when they meet, we get no displacement, right, during that point, because we have completely destructive interference. Now, an incident wave and reflected wave can be thought of as merely a repeating pattern of crests and troughs, right? Trough, crest, etc. One's heading this way, one's heading this way. And since we have the crest and the trough, what's going to happen is if they can meet at a point where they're going to be make it look like one wave, then that's what a standing wave will be. So the importance of timing, and you can see here with this animation that where the blue and the green meet, where they look like they're standing still, right there, right there, right there. You can see the black one. The black line is the wave that's formed from the interference. So we have constructive and destructive interference, but in the end, when we have completely destructive interference, that's where things meet. Now, if you look at these points where the N and AN are, the points in the wave, the standing wave, where the particle doesn't appear to move, so I'm going to draw that right here. That's what we call a node, okay? These are nodes right here, 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 and here. There are points that vibrate back and forth, a large positive displacement, and that's where we have our really good interference. And these are our antinodes, okay? So nodes are where we have completely destructive interference, and antinodes are where we have completely constructive interference. So those are the two things we look at with the timing. Now we do that to introduce a crest at an instant that another crest is either at the halfway point across the medium or at the end of the medium. Okay? Regardless of the number of crests and troughs. If a crest is introduced at the instant another crest is undergoing its fixed reflection, a node will be formed. Okay? And then when we see the node, that's where things are completely destructive. The number of other nodes that we present on is dependent upon the number of crests that were present between the two timed crests. So the more crests we have between the two timed crests, the more nodes we're going to see. If a crest is introduced at the instant another crest is at the halfway point, then an antinode is formed. And that's where we have completely constructive interference. And it'll be formed in the middle of the medium by means of constructive interference. In such an instance, there might be nodes and antinodes located elsewhere along the medium, okay? So that could also happen. But when we're trying to make one, to make a node, all right, to make a node, we have to have the crest is either at the halfway point. We have to make a new crest when the other crest is either at the halfway point across the medium or at the end. And then when we talk about an antinode, it's when another crest is at the halfway point across the medium, okay?